very confused on that one, yeah.
Alright, so, question on conditional sum. Now, we talked about briefly in there, so I won't go through it. Technically could be a fair game one. Less likely on my list of things just because we didn't put as much time on it. There is a video on it also online already. But the basic idea behind conditional sum works this way. When you've got, I think it's best with an example. So, you want to pick two numbers for me?
How about?
Yeah, what's that?
No.
3 and 5.
3 and 5? Okay, so let's do it two ways. Let's do it kind of the traditional way and watch how that would function as it's going in. So when you're looking at this the traditional way, and then we'll show a conditional sum, and then I can, you know, from the kind of traditional way, I can mention to you what a carry look ahead would do. So the idea of this is for these, with the regular one, you pass this in, and the XOR gate is, you know, going to take this and this, and you run into an XOR, and it's going to give you your bit, and then it's going to take this and this, and you run into an AND gate. So, you know, we'll get our 0, 1, and same thing carrying through all these XOR together, and I'll get 0, and then and then OR them, and I would get another 1, 0, 1, so on, 1.
Yeah.
And you find 3 and 5 gives you 8, and nothing carries out, your final carry goes out. You know, with the ripple as it goes through. When you break those same ones down to do the conditional sum, the name kind of gives it away, and I'm giving myself a little more space so that I can handle each one of these. What we do for this one is we're going to go and build these as if we knew what the carry bit was. So I'm going to generate kind of two numbers. So just for convention, to save myself a little room, this is the one if the carry was a 1, this is if the carry was a 0. All right? So the difference between these two sides should always be different by 1. This is always 1 bigger. So what I'll basically do is I'll just add the two numbers and put them here, and then for this one, I'll just add 1 to it. So first I'll just kind of walk through on all of them. 1 and 1 gives me 2, 0 and 1 gives me 1, 0 and 1 gives me 1, 0 and 0 gives me 0. Now for the first one, I know what the carry is, so I don't have to generate 2 of them. So I'm only going to generate 1 number there, because I don't need 2. Now you could if you wanted to, I mean, because technically speaking in add or subtractor, you could have different ones. So you could say, hey look, that's 3 if it was a 1 carried in that's going on. But it's worth knowing I would know that in advance. So you could do it either way and select at the end, or you could do it right at the beginning. What's going on? I'm going to go on the what we talked about in class, then I could just select this in advance. But for the other ones that goes in, I don't know what the carry bit is simultaneously. So I'd have, 1 plus that extra 1 would give me 2, and 2 there, and I'd either have 0 or 1. So what you're getting is, what if the previous state had not carried to me, what if it had for each one? Then all we do is we just group them up. Because at this point, I do know this is the sum bit and this is the carry bit. So at this point, I know what the carry bit is. And all these are generated at the same time. And since the carry bit is a 1, this was what if the carry was a 1. And this is what if the carry bit had been a 0. Well, I know the carry bit's a 1. So that means I just grab the ones that are here. So it should be 1, 0, and then the sum bit doesn't change. Just grab that one and bring it down. And this 1, this is like a multiplexer coming in. What if it was 0? What if it was 1? So I literally just run this bit right in, and that generates these two. Just copy it down. That's going on. And in this case, there's no options. Now here, I don't know which of these two numbers is going to happen. Right? So I technically have to handle the carry bit for both. So the right side is going to generate the right side here, the left side will generate the left side. So in this case, it's a 1, and it comes down. Here it's a 0, which means I select this one. In this case, the 0 comes down, and it was a 1. So the 1 tells to select this number, 0, 1. And just like I mentioned before, this one is 1 bigger than that. There's number 2, there's number 1. So just sanity-wise, it should always be bigger than 1 by 1, because all it is did you add 1 or not add 1? But notice I can do those in perfect parallel. So it didn't really cost me any extra time. It cost me a little extra space, but it didn't cost me extra time. So I just have my options still open. Well, on this one, this is the 2 sum bits, and that's the carry bit. So now I know which one to pick. So the 2 zeros just come down. And then this 1 is selecting between these 2 again, just like we did before. It's a 1, so it's going to select that 1, which is going to carry over, and 0, 1, 0. So that's my 4-digit answer, and that's the carry out. And if you notice, that's my 4 answer, and that's my carry out. So it generated everything you normally would have generated. The difference being that when it was going on through here, each one of these steps involved 2 gates per step, and then had to carry through. So I had 2, 4, 6, 8. So it took me 8 gates to get through. That was going on. So this took 8 gates that was going on. To generate these numbers that was in here, in these cases, I was only adding 2 things together. So for most of these, it's only 1 gate to generate them that's going on. Worst case scenario, I might have 2 gates when adding the 1s on. But I'd have 2, and then at each of these steps for the muxes are 2 gates deep. So I had 2, 4, 6. So this one was 6. And you might look, oh, 6 versus 8, not a huge difference. But if I were to take this one and go from 4 to 8 bits, all I'd be adding is 1 more layer in this tree. So this one to go to 8 bits would go to 8 gates deep. This one to add another 4 bits onto it would double the size of this, so it would go to 16. Right? If I were to take those 8 bits and now go to 16 bits, this one would again double and it would go to 32, but this would add 1 more gate, or 1 more mux level, which would go to 10. Right? So as you start seeing, as you're building up here, we're doing 4 just because it's easy for a human being to do. But as it goes on to machines, you can see it's not a lot that's going in, and you figure you can do usually pretty easily 4 to 8 gates in a clock cycle. So for most of this, those ones can rapidly get to multi-cycle, and this one's hovering right on that 1 cycle edge. It's going in. So it becomes a much more reasonable prospect to finish going in. And just like before, since it's a regular adder, you can do a subtractor without any difficulty. Right? Because the carry in, right? 1 for a carry in just does the subtraction. You just flip one of the numbers. So it'll do the 2's complement, so it'll work normally. The only difference when you go to carry look ahead is you generate all those carries, the 1, 1, 1, 0. You generate those in advance, and a couple levels of logic, and then you feed it in there. So it takes about 4 gates to do, but it doesn't matter how big it is. But now the gates become more and more expensive to build. But I can do it very, very fast. there and write your trade-off.
Okay, I kind of have a question that wasn't one of the midterm questions, but when you went over in class how to convert avogadros, I was the avocado, was that right?
Avogadros. Yeah, so when I was doing that one, when we were going through it, I completely forgot to include the exponent on it.
Yeah, so then how would you add an exponent that was
So, on that one, that would not be a particularly great one to do, right? So let's say we had 6.023 times 10 to the 23rd. You would technically have to take this and it would become 6.023, right? There's 3, another 3, so up to 6, right? You'd actually get
And you
this
divide
int,
that
and
by
then you
2
convert
until
it.
you found.
So, now, the division by 2 is kind of easy for a human to understand, but there are other ways you can convert numbers. That's
Okay,
going on.
just checking.
But yes, it would be, literally, you'd have to be converting that as it
Okay.
goes on.
Because there's no way to just find the exponent base 2 from an exponent.
Because the thing is, you can approximate them, but to get an exact is a different beast. So, if you consider 2 cubed, that's 8, which is pretty darn close to 10. And so we do similar things like this. We go, okay, 2 to the 10 is 1024, which is pretty close to 10 cubed. All right, so these are where we get those approximations, but it's not exactly, okay? So we can go in, and it's based on this process, 2 to the 20. This is where we get the, kilo, meg, gig is based off how many bits as these goes. Because if you take that number and square it, again, you're gonna be pretty darn close to 1 million, but, you're still off on one of those places. So, I mean, it's an approximation. So a direct conversion from that would be,
Right.
not efficient. You would end up with another floating point number that you'd have to convert. You might as well have just,
So we shouldn't expect that to see that on the exam.
well, so I will not pick exponents
decimal.
I could do something, that was like a, 3.2 times 10 to the second. I'd have no problems with, something like that, or, I could do it to the -2,
Yeah. Okay.
right? But it'd have to be small, because you have to convert it as it goes in.
Makes sense.
Just time-wise, it's just not practical in that thing, particularly without a calculator or something to have to go through, so. And I can guarantee you, unlike that one, it will work out, it will terminate. That goes on. So if I give you something, it will be a number that will end in a few, that you'll see pretty quick. Usually it's, 4 or 5 multiplied by 2, it's gone. Type of a thing. So.
Okay, so on the homework that was due today, the quiz that we were doing, one of the examples, I'm trying to remember specific numbers, I think I have them, I did it on scratch paper. But one of the final questions was after we had converted, we did Booth's algorithm to multiply -4 and -5. And then we did it where we switched x and y, and I got both of those correct, but then when we were supposed to, oh no, and then we converted the decimals, and then we had to add the 2 decimal numbers together. Is that making sense? So we had decimal
Well,
numbers.
The boost one and multiply them, I mean, maybe I gave you, I wrote those questions like a year ago, so.
Yeah, well, I think what I missed on those, you said to write down the value for u after the third, what are they called, like third step or third rotation or whatever. And so I didn't know if that was after you add, like if it's a subtract, do you do the subtraction and then put that value as after the
So if I
rotation?
said after the third, it should be after the end of the third, but before you start the fourth.
Okay, so then where does the subtraction come in? Is that during the third? Or is that?
So the
sorry.
process that you do is you, based on whether you see the pattern 1, 0, or 0, 1, you're either gonna add or subtract. That's the first part of that cycle. And then there's the shift.
Okay, so after the shift.
So this
you
is
do-
kind of step 1, this is step 2, and you repeat that over and over again.
Okay.
So you would do both of these for 3 and then tell me what you got.
Okay,
That's kind of my way of checking that you did the work.
Okay, but if it's
Right,
after the
because
shift,
it would be very easy to take a look at it and just do -4 times -5 is 20, convert 20 back, right?
yeah,
And so you don't have to actually do Booth's algorithm to do it. So the reason why I asked for a middle step was that way I could see that you actually did the work. Because
Yeah.
I don't think, if you could just tell me de facto the reversing of it, you know, then you probably know well enough that I don't need to test it,
yeah,
so.
okay,
And there's no easy way to make the computer check every step of Booth's algorithm inside Canvas.
okay, yeah, that's fine.
So, well, that's just kind of, a little bit is the psychology of why is it there and what's it doing. And the thing is to make sure, I want you to know the steps, not because I care that you can do the steps, but if you can't do the steps, you can't build a circuit that'll do the steps.
Yeah. Okay, so the other thing that we had to do was we converted 2 decimal numbers to binary, and then we had to add them together. So when adding them together, can we leave the exponent that we had on the binary number the same, and then just add the base numbers?
So if you just have 2 integer numbers in
Yeah.
binary,
Yeah, or double, well, integer doubles, whatever they are with decimals on them.
doubles.
So yeah,
Okay.
there was 23.21875 and then 16.03125. So we converted them separately to binary, and then you said to add them together. And so once we've converted them to binary and we have like the exponent and the mantissa, can we leave the exponent the same and just add the 2 mantisses?
So for addition, you always take the bigger of the 2 exponents
Okay,
and you redo the other one to that. So, I mean, imagine I was gonna take, you know, let's just do a quick decimal version. Say I was having 1.53 and I wanted to add to it, let's say this was times 10 to the 2, and I want to add, you know, 7.2 times 10 to the 0. That's going on. What I would do is I convert this one so it's at 10 to the 2.
can you do that easily from binary?
I can just take the number as it sits, right? I take that by making it smaller there, I've got larger than that, the same. And then I can just add them. So in this case, I get 1.602. Because now they're lined up, so I can just line up the radix points.
And that's easy to do in decimal.
It's no different in binary. Right? So in binary, if I had, let's say I had the number 0, is it okay if I write the exponent just as a decimal number for what's going on? So let's say I had 130, and then I'll do this one in actual bits. So we're going on.
Why 130?
Because 127 is the point for 0, so I'm picking something a little bit bigger.
Okay, so 3 is our exponent now? Okay.
So, well, we can, that's 128. So, yeah, 130, we'll put it binary. And the reason is that this one puts it 3 bigger, so it's times 2 to the 3rd, so it's, you know, on the order of 8 to just shy of 16 as a number. It's picking on, and then we can go 0, 1, 0, 1. And the rest will be zeros. And then I can take the next one and add 0, and let's just like 127. And for this one, we'll do fair. Okay. So if I'm going to add these, I've got to get them so they're, just like I did before, a common multiple as it's carrying on. So the number that I've got here that I'm adding is 1.0101 times 2, and just like we said, we knock 127 off it, so times 2 to the 3rd. That's what that number is. This number is 1.11. I point the hidden bit back in just like I did before, times 2 to the 0, because that's 127. So 127 minus 127 is 0. So I'm gonna want this to go to a 3, but that means this has to get smaller appropriately, so I have to shift it by 3. So then I just line up my digits by lining up the radix points, and then I can add. Right? So by lining them back up again, I've got 1.0101, and this one gets 0.00111. And these are all times 2 to the 3rd. So now I just add them. I get 1, 0, carry a 1, 0, carry a 1, 0, carry a 1. Alright. That's the hidden bit, so this is my new number. I stick that into my answer part, so I get 10001, the rest zeros. It's still times 2 to the 3rd, so I just keep
Keep
my
the
answer
bigger
part.
one.
And it's still positive.
Okay.
So that kind of process there.
Okay, so
That-
it still feels like we're adding it in decimal, but it's binary.
That's just scientific notation.
Yeah.
All we're doing is we're picking a particular way of ordering them, because here, it's kind of easier for a human because the numbers group in a little more logical sense that you're used to. You know, this one just always seems freaky because it's just a string of bits.
Mhm.
But really, to the computer, you know, it doesn't care where they go, and it can't handle the shifted and everything else. It wants everything in the sequence, as long as it knows what that sequence is.
Yeah.
So I just took it from the format it had and put it into a more human palatable, but I didn't change the number. You still did in binary. And the point that I'm trying to get across in all these is that it's really not any different what we do in binary than what you would do in decimal. It's actually easier because we only have either zeros or ones.
Yeah.
So the process is actually a simpler process. And if you just pull your experience from here across, it becomes easier.
Okay. Right, I've had a class. But thank you, and then did you say you'll be in your office today, or?
Well, I'm gonna be here till 3-something-ish answering questions.
Yeah, I'll be in class.
And then I have to sign my daughter up for, she's going into high school, so
Oh, cool.
Yeah.
What high school is she
So-
going to?
transferring.
Okay. Okay, I've heard about it. All right, well, good luck. Thank you very
Okay,
much.
thank you.
So can we just like ask? general
Whatever you
questions?
want. You ask questions, I answer problems.
I was kind of wondering if you like go over maybe converting MIPS instructions to like C code.
Okay.
There's like,
So do you have a sample of something that was confusing?
I was just like looking through the problems in chapter 2, and I think if you just like go over problem 210, I have it right here.
So if you read it out, I'm happy to.
Or did you want to?
I don't have my glasses on me, so
Okay.
the likelihood of me reading that small print is
Yeah,
probably
yeah.
low. Now, just for your knowledge, I'm happy to work that problem, but we'll probably go the other way, MIPS to C, not C to MIPS. I think most of theirs was C to MIPS. Is this a MIPS to C thing?
Yeah.
Okay, awesome. Then that's very appropriate. Okay.
So it has an add if immediate, and then T0, S6, and 4.
And S4?
Just 4.
Oh, right, it's an add immediate. Okay?
And then we have an add, and then it's T1, S6, and then it looks like the register 0. Is that?
R0?
Or the dollar sign.
Dollar sign R0.
Okay, sorry.
Yeah. Yeah, whenever they put a dollar sign, it means it's a register.
Okay, that's the same. And then for the next line, SW, T1. And then it has 0 and in parentheses, T0. Then we have a load word, T0. And then it's a 0 with parentheses, T0. And then the last one is add. And you got S0, T1, and T0.
Okay.
That's it.
So if you notice right here, a couple things when I first start looking at these. T0 you can see is inside, so this is the base address of something that's going on with an offset of 0. So that's telling you it's looking into memory at wherever T0 is pointing at. So this calculation that's going on here is calculating the location of where to go. So when it's doing this store here, right, does it say what S6 is, or do they just tell you?
They just tell you. Oh, they have so assume that the variables F, G, H, I, and J are stored, are assigned to registers S0, S1, S2, S3.
F, G, H, I, J, and they're stored to
S0,
S0.
S1, S2, S3, and S4.
It's kind of funny because not one of those is one that they're using.
And then it says, assume that the base address of the arrays A and B are registers S6 and S7 respectively.
Okay. So we've got an arrays and that's it, and that's as far as they tell us?
Yeah.
Okay. Okay, so we're assuming at this point that there's memory out here, right? Now, you notice we're doing S6. And so the array A is here, and this is in S6. So by doing S6 plus 4, they're taking one element down. So this element would be A0, so this is A1. So when it's doing this calculation, it's putting into T0 the address of A1. Does that make sense?
Yeah.
Okay. And then on this step here, it's taking S6 and it's an R0 or $0. So that means add nothing to it and put into T1. So what that's doing is putting the address into that location. So it's copying S6 over. And then it's taking store word is going to store that address into T0, which is what we just calculated here. So it's going to store here the address of A into that location. And then it's loading that word into T0. It's kind of an oddball way to do this. This is, so that's gonna, now we have that T1 is equal to S6, and T0 is now gonna be equal to S6 because it's loading that back up. That's going in. And then S0, which is our F, is gonna have what we just loaded back up. T1 and T0 are both now contain A. So it's gonna be, A plus A, the pointer A. It's not a particularly intelligent calculation. So I'm not sure why they want to calculate this, and there's a lot more efficient ways to do it, but that's in essence what it's doing.
Okay.
All right? So usually they try to pick reasonable code segments. I'm kind of curious what they're. So given what they're saying, that's what it is. So if I were to put this into, kind of a C-like syntax that's going in, technically speaking, multiple of these are carrying to one area. So, when you're calculating this part here is saying A1, and it's becoming equal to what's in T1, and T1 is the pointer to A, which there's a couple ways you can do it, but that's one way you can do it. Fine. So, because that's all this is doing, that's just the pointer to A. And so that just stick it into T1, and that gets copied over. So the first three are doing this. And then this one is putting back into T0, which is being added, so S0 is F. And F is getting T1, which is what was here, which is your pointer to A. And we're adding to it T0, which is what was in A1. I mean, it's a really ugly way to just double the pointer. But, that's what it's doing. So that would be kind of, if I were to summarize it. Now, there's a lot of C syntaxes that you could use to generate those. I could do a line-by-line equivalent of each one. But in this case, it's kind of a little more efficient to group them up into what does it mean.
Okay. And so with the store word, load word, so that's the offset, the number in front of the parentheses.
So this is base address plus the offset.
Okay.
And your offsets here are 0, so it's not doing anything.
So those be multiples of 4, or just depends?
So it depends on the data type you're storing.
Okay.
In this case, we're doing a word, and so words are by definition 4 bytes.
Okay.
And this is based on bytes, so it's grabbing 4 at a time. That's why when it went down 4 here, it was going down 1 word.
Okay.
And most ints are 4 bytes long, kind of your standard int size, which is why I was saying this is likely an int that's in here, and so I was going from A0, the first entry, to A1.
Okay.
So do we have other questions? So basically the way I do the tutorial
Yeah,
is
just
you guys ask
question,
questions,
yeah.
I answer questions.
Okay, it's not super specific, I guess, but I'm a little bit confused, a little bit on the multiplication stuff. So,
Which one, integer or floating point?
floating point.
Floating.
Yeah, sorry, that's not very specific, but you.
Why don't we do an example?
Yeah, let's do that.
Why don't we work our whole way through one full thing? We'll start with decimals and then we'll go all the way around.
Okay.
Fair?
Yeah.
Good first number?
Uh-huh.
You guys want to pick a second one? We basically want small ones that will terminate nice. So I kind of picked 3.5 because it's kind of a nice, easy number. You guys got a preference on other, or you want me to pick something?
4.2, is that not gonna terminate nicely?
It will if you let me put a 5 on the end of that.
Good, sounds good.
So we're going to take these and we're going to first convert them. So let's do the 3.5 first. So if you remember when we deal with these, we did 3, we do a series of divide by 2s, decimal point. This will be the multiply by 2s, and then over here we've got the 0.5. So 3 divided by 2 gives me 1 time carrier 1. 1 divided by 2 goes 0 times carrier 1. 0.5 times 2 gives me 1.0. As soon as you hit the 0 here and the 0 there, you stop. There's nothing else to do. Right? Because I can keep going. 0 divided by 2 is 0.0, but And same thing, take, 2 times 0 gives me 0, 0. That's boring at that point. So we just read it around, and that tells us that 3.5 is 1, 1.1. 1.1. Now I want to put this into floating point notation. Floating point notation wants that radius point over. So I made it smaller, I divided by 2, which means I've got to multiply by 2, otherwise I've changed the number.
Wait, so you just multiply it by 2? I see what you're saying about you're moving over.
Because shifting that decimal,
Right, it's like
or
multiply by
shifting the
10,
radius was just like, yeah, but these are
But it's
binary.
2, yeah.
So every time I shift this way, I've divided by 2, so I have to multiply by 2. Otherwise, it changed the number. And all you've got here is, once I shift that radius point, it's 1.75. That's what that number is. Right, because that's 1, that's a half, that's a quarter. Right? So 1 plus a half is 1.5, plus a quarter, 1.75. 1.75 times 2 is 3.5. So I haven't changed anything. Right? But I have to get it so that there's a single 1 to the left of the radius point. That's scientific notation.
Wait, why would we do times 2 to see?
Because my original number was 3.5,
Yep.
right? Because this is the 2's place, the 1's
Yeah.
place, the halves place.
So that's 2.
And this is the 1's place, the halves place, the quarters place,
Yeah.
right? And 2 to the first is 2.
Oh, yeah, okay.
Right?
Yep.
So 1.75, when you add these up, right, half and a quarter is
Yeah, I was-
3/4.
Yeah.
Right. So 1.75 times 2 is 3.5,
Yeah, it's
which
like
is what our
5.
original number was. So it's the same thing that you do in decimals, except our number is 2, but who cares? It wasn't anything magic to decimal, it was magic that it's a base position number system.
Yep.
Okay. So we feel good with that one?
Yep.
So we've kind of got, this is our number that we're going to be dealing with for multiplication. Now I can take this, I can put it right into my IEEE format. The first one's the sign bit, it's positive. Okay? The second one is the exponent, which is going to be my exponent, but I have to add to it 127. Because we did that excess code, we're going to take and add those together, then we're going to store it in here. 127 plus 1 is 128. 128 is a power of 2. So it's kind of nice for me already. So it's 128, no 64s, no 32s, no 16s, no 8s, no 4s, no 2s, no 1s.
And how many bits? is
Eight.
it?
So we're just doing this in single precision. So there's 8 bits. So nicely, 128 happens to work out very cleanly for me.
And why do you,
So the IEEE standard is to store whatever that number is plus 127.
okay,
And that allows the negative numbers to be less than 127,
oh, yeah.
right? And so they're now all nicely sequenced.
Oh, yeah, that's what you're talking about, I think, with looking at the first number. and
That's why they do it, so you can just start looking on the things, and each digit as you walk down, that's the most important to tell how big or small it is. That's the next most, the next most. You can just walk down them.
Makes sense, okay.
So it's very easy to do size comparisons by storing it in this format. And so the only thing that's left to store then is this number, because we always know it's 2. We're in a computer, it's binary. And we said this digit is the hidden bit. Since it's always going to be a non-zero to the immediate left, I only have 0 or 1, so it's got to be a 1, so I don't need to store it. So I only have to store these 2.
Because if it was a 0, you just move the decimal.
I move the radius, that's the whole reason I had to move this radius point. There can only be one 1 to the left, and it must be there.
Yep,
So, there's no reason to store it, so I'm just going to store those 2. And you know the other ones were there, so I've got as many zeros, I could have added zeros to the right here as much as I want.
And then fills up.
I got a half, a quarter, I've got no 8s, I've got no 16ths, I've got no 32nds, I've got no 64s, I've got no 128, you know, I can keep going, right? So you can always stick more nothing to the right. That's just like saying, if I gave you 52.1, have I changed the number? Right?
Yeah.
Add as many zeros as you want there, you add as many zeros as you want here, that's not a base 10 thing, that's just, you can have as much extra nothing as you want.
So what is that though? Is it, how many do you add? Is 32 minus 9 there?
Yeah, so that's, you know, 8 plus 1 is 9, off 32 gives you 23. But I would perfectly accept this. If you just told me, hey, there's 23 here, and you did the 1 and 0, dot, 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 0, I know you were filling in zeros.
And what's that number called again?
It can either be called the significand or the mantissa.
Okay.
So I'm using the term mantissa just because this is the sign bit, and being really lazy, I like to call this S, E, and M. And if I call this a significant, I'd have 2 S's.
Mm-hmm.
Then it wouldn't be unique. So,
This is single precision, right?
this is single precision. So I'm not gonna worry about double precision on this. It doesn't, double precision, the only difference is it's 1 bit, 11 bits, and now that adds up to 12, off 64 leaves you 52 bits over here. But other than that, it's exactly the same. Well, you don't add 127, you add 1023.
So
I mean, that's just
that'd
the
be for
addition
bigger,
difference.
bigger numbers.
It allows for a bigger range of numbers.
Yeah, but less precise.
Well, actually, because I'm giving you more 52 bits plus a hidden, so you get 53 instead of 24. So
Oh, it's,
you get more of everything when you go to double precision.
oh, it's.
Because it's
using a-
twice as big.
Using a 64 bits? Okay. I didn't realize you were shooting.
So that's the double precision. What he was asking about, you know, what if it was double?
Okay.
But so some people like doing double, some people like doing single. I like doing single just because it's smaller and it's easier for you to calculate. And honestly, you should not be doing these in your head, you know, what's carried out. There's better ways for humans to do them. The reason why we need to be able to calculate this is not because you need to be able to calculate in this area. You need to be able to calculate to know what it is you have to build as a circuit. Right? And so if you don't know how to do the calculation yourself, you can't build a circuit to do that. So the only purpose for it in my mind is to get familiar enough to build it. But you can figure out how to build it off single precision.
Yeah.
You know, at which point, if you need to build double precision, it's just bigger versions of the same thing,
Are you gonna go over the building the circuit with it?
if you want me to.
Yeah, can you?
Sure. Okay, so we got our first number. Is it okay if we now do it for the second number?
Oh, yeah.
Okay. Is it okay if I just kind of erase that one and we
Yeah,
can do
you
it in
can
the same
say-
space?
Yeah.
Oops, should erase that too. Now we'll do the 4.25. So we go 4, series of divide by 2s, radix point, series of multiply by 2s, and 0.25. 4 divided by 2 is twice, carry nothing. 2 divided by 2 happens once, carry nothing. 1 divided by 2, nothing, carry 1. As soon as I find that 0, I stop. Now I do the other side. 2 times a quarter gives me 0.5. 2 times 0.5 gives me 1.0. As soon as I get that 0, I stop. Just read it like a horseshoe. 100.01.
Mm-hmm.
I gotta move the radix point 2 places. Since I'm moving the radix to the left, I'm dividing by 2, 4. I've gotta multiply by 4. Divide by 4, multiply by 4, no change.
Mm-hmm.
So, this is your hidden bit. That's the mantissa. This is my exponent, which I'm gonna have to add 127 to. And I'll store that in my next number. Now I have everything ready to write it in. The sign is positive. My exponent is 2 plus 127, which is 129. 129 is 128, plus no 64s, no 32s, no 16s, no 8s, no 4s, no 2s, 1 plus 1. Now you're welcome to actually do the normal division if you really want to, but I think it's quick and easy enough to do for these ones. And then I take the 4 non-hidden bits, 0, 0, 0, 1, I write them in, and everything else would be 0, and it's still the same 23 bits. Good?
Yeah.
Okay. So, we now want to kind of do these, or take care of it. Now, when you're doing the circuit to build it, the easiest way to remember it, I think, is to think of it in terms of how we were writing them over here. So, I'm going to remove some of the ugliness here. Now, the number that I had stored for this one, that's 129. So I had taken 129, but I had added an extra 1%, so it really has to kind of subtract that. So that the actual number I had was 2, which 2 is 129 minus 127. But that puts it in the thing of knocking out what my actual was. And then this being what I stored there. So these digits just came right from here. And then this gave me the 129. So if I was actually working on it, that's what I'd be working on. That make sense?
Yeah.
Okay. So this is my 4 1/4 number. If I look at my 3 1/2 number that was up there, it has a hidden bit and then 2 1s. And it's times 2 to the, that's 128. But everything was stored excess 127.
Yeah.
Make sense? Now, we're multiplying here. That's going on. Now, technically speaking, each of these ones is also times -1 to the 0, because that's the sign bit. Since they're all multiplied together, I can commute and associate freely. That's going on. So I'm going to commute them so that these two are right next to each other. And then I can use my law of exponents, -1 to the 0 plus 0, which is addition. Now technically if it was 1 plus 1, I'd get 2. But I don't really care whether it's, -1 to the 0 is 1, 2 to the, or if I had -1 to the 2, it would also be 1. Any even power actually is going to work. So all I really care about when combining these two bits is not the final summation. I only care about whether it's even or odd. That makes sense? And the even or odd is determined by the exclusive OR. So I'm just going to exclusive OR those two. Because that'll just give me the part I care about. Because
Yeah, even.
right? I mean, are you really going to take -1 and multiply it out, 256,742 times? Or are you going to just look at that and go, it's even. -1 to an even power, it's 1. Yeah. Neither would I. I mean, so if I went up there and, remultiply stuff, no, you're just going to go, it's odd. It's -1.
Yep.
That's all you gotta do. So all I have to worry about is, it's kinda hard to read there, putting the exclusive OR gate.
Yeah.
Which does kind of tell me is it even or odd. That's really what exclusive OR calculates. So when I'm looking at these, that means if my answer's down here, means I'm just taking these first two ones and I run them into an exclusive OR. 0, exclusive OR 0 is the next easiest one to deal with works off these. And again, because that whole lovely, commute and associate, and then I use my lovely powers, they both have the same base. So what I end up with is 129 minus 127 plus 128 minus 127. You agree? Just taking those two and adding them. But I always store everything in excess 127, which if I regroup that here, it's that sequence minus 127. So that must be what's stored then. 129 minus 127 plus 128. So circuit-wise, I could just add these two together and then subtract 127 from it. I can just take this one and this one. When I add them, that's 129 plus 128.
What was the last thing you said about why you can do it differently?
Oh, because if you notice, every time we did what was stored minus 127. What was stored minus 127. That's just what it is, because we stored it in excess 127. So if I'm getting the final answer in this format, it's the same as what I'm going to store minus 127. I just kind of regrouped it. Since I haven't, I just had one extra minus 127, so I better subtract it out. That's part of the calculation. I'll put a negative 127, which lets me add, or if you prefer, you could just call it a subtract or put 127. I don't care which, whatever makes you happy. It's the same thing. So I guess I ended up there. I'll leave it there. So what's going to come out of here will be that. Now remember, we said we have to check to see does this end up shifting any. So I can't finalize this answer yet, because it's possible that this could end up being 2 or bigger, in which case I'd have to shift the radix point. So, but that's pretty darn close, within 1.
Yeah.
So we have to do this last part, and this is just normal multiplication. So for this one, I'm just going to take the two numbers, and I multiply them, and I get my answer. And then I'll have to take the leading bit and determine was it 0 or 1, should it shift. So let's actually just take these and multiply. So we've got 1.0001 and 1.11. You can do this whatever way makes you happy. You like the usual way people multiply. So I mean, you could do it kind of like you do in grade school and so on. You could just go, 1 times that gives me 1.0001. 0.1 times that, it just shifts over, just like you put the zeros before. You can do the same shifts. 1.0001, and that one shifts it one more time. 1.0001, and then add them. So just like you shifted the other direction when you're going bigger, you can shift that direction when you're going smaller. That's an acceptable way to do it. In which case you'll find you get 1.110111. It's a perfectly fine way. You can also do kind of a shortcut. Technically speaking, this pattern, every time there's a 1, you copy that pattern with where the 1 is the number just to the left. So in each one of these spots, I could go, oh, here's a 1, so I'm going to have 1.11 there. There's a 1, I'm going to have 1. 1, 1, but I don't need the point there, and then there's an extra 0. And you'll notice it's the same stupid pattern. There's like a million ways you can do these. It's like all multiplication, there's tons of little shortcuts. There's even more shortcuts because they're binary, and I don't have to worry about scaling when adding them. So the number of cutesy little tricks you can do is huge. I don't care, whatever makes you happy. You can even do I think some people actually count the radix points out and then multiply them in int and then shift them back. You can do that too. That one will work perfectly fine also. Yeah. I think that one's the slowest and most tedious, but hey, you know, it's not gonna actually hurt us, right? I could shift out, I got 4, 5, 6. So I could go, you know, remember that there's 6 shifts and we got that and that, and you can multiply. You get 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, just multiplying each one through. Add them up. 1, 1, 1, 0, 1, 1, 1, and then come back 1, 2, 3, 4, 5, 6. And you'll notice 1.11, 0, 1, 1, 1 is the same there, is the same there. All 3 tricks, all same answer. Doesn't matter whatever way you feel comfortable doing that, it's just like integer multiply. So for practical terms, I could just grind into an integer multiplier like Boost algorithm. There's even faster ones than Boost, but you know, for our terms, simple enough to just say multiply will work for sure.
Should you not just take 3.5 and then multiply it by 4.25 and then convert that to binary and then do like the basic step for switching to the IEEE format, which is like instead of multiplying out the whole thing like that? Do you have to multiply them in IEEE format?
So how would you convert it to that? I mean, this is what you're trying to do, but you're inside a computer now. And you're trying to think, inside the computer, what does the computer have access to?
Okay.
So what you're saying is, could the computer, it would have to take it, put the numbers out, ask you to multiply and enter the numbers back in, and it'll convert and put it in the spot.
Okay.
Right?
Yeah.
So what we're trying to do, we're going through this ugly thing, not because I want you to do this, right?
Just with,
You're learning it enough so you can figure out what has to be done so you can build a circuit,
okay.
right? Our goal is not to do this repeatedly.
Mhm.
Our goal is to learn it, to find the equivalent, to build a circuit, to make a machine do it so I never have to do this again, right?
Mhm.
You know, so if you do it the other way, yes, it will work because you're doing the work.
Yeah, yeah.
You know, but then we have to do work, and that's work, right? So, I mean, we want to build machines to do them.
Okay, that makes sense.
Can you explain what forwarding is again?
Can I do it as soon as I finish this for them?
Yeah.
So, yeah, I mean, happy to explain forwarding. Okay, do we feel comfortable with this, how you can get them? All right, in this
Do we need to
particular
build a
case,
circuit to do that specific, like every step in there? Like
can I
on the
build a
board?
circuit to do that? I mean, that's,
Well, no, I know
notice
there
this
is
is
one.
just integer multiply. That's what Boost algorithm did, right?
Yeah.
Boost algorithm does integer multiplication. So what I'm doing here, you could just put into Boost algorithm and it'll calculate it, and we showed how to build a circuit for that. So the idea is this is why we started with the integers, because we first did how's different ways you could do addition, right? Now that we've got adder units, we can just assume I've got an adder because I've built it, right? And we know how to build them. We know how to build different ones, and you can pick the one that's the correct speed. You know, now I want to take an adder and I want to build multipliers. So we talked about doing the kind of standard pull the sign out way, or you could do Boost algorithm, you know. So there's a
That's
bunch of
what we
different ways
put
to
into
multiply.
that.
We built it. Then we have a multiplier, an integer style multiplier.
So that's what we would put by that, we're in that circuit right there.
So, yeah, you could, so this could be Boost,
Yeah.
for instance. Usually we don't because Boost isn't fast enough for us, but you could, right? We want to build them as fast as you can. There are some really crazy fast ones you can build that's going on. But you could put a Boost algorithm. These are just adders and subtractors. We've already built those. Right? So every one of these things has to be something we know how to build.